Welcome everyone. In the next 20 minutes, I want to talk about scalable n-way model matching. And this work is a result of a collaboration between Humboldt University of Berlin, Ulm University, and the University of Bern. And my collaborators are Maximilian Bittner, whom you just saw, Thüm, and Timo, Kehrer. Why do we need model matching in the first place? Model-driven development is crucial in certain domains, such as avionics, automobile, or rail transport. And in these domains, multiple model variants are created to address the needs of similar systems. And a novel model is created by cloning and owning an existing model to fit new requirements, which simply means it is copied and modified. As a result, there are multiple model variants sharing a significant number of similarities between them. And for different development activities, we want to identify common elements, for example, in order to unify separate models later on, or in order to synchronize changes in common parts between them. And thus we want to match models themselves. Here we consider two types of model matching algorithms. First, pairwise matching, and second, n-way matching. In pairwise matching, two models are considered at a time. And the elements are compared one after the other. And as a result of this first iteration, these two models are then merged. This is often just done virtually, so there's no need to merge the actual model files. Later, this merged representation is compared and matched to the next model inline. So we have a chain of model comparisons and matches. On the other hand, in n-way matching, we consider all models at the same time, and therefore we can consider all elements and all possible combinations of elements at the same time. Now, let's have a closer look at this difference between these two approaches. As I just said, in pairwise, we have a chain of model comparisons and matches. While in n-way, we see more or less a fully connected graph if it's done naively. And the problem here is, of course, that it does not scale well because we need a lot more comparisons than we would need for a pairwise matching approach. So why should we still try to do n-way matching in the first place? Well, the problem is that pairwise matching, we have to decide on the order in which the elements and models are compared before we start matching. So we have to somehow put the models into an order. And this ordering problem is not easy to solve. And it can be the case that, for example, here, model number 0 and model number n are highly similar. And by comparing them first, we would be able to form really high quality matches. But because we consider a lot of other models before we even consider model n, there might be worse model matches formed. But why do we need scalable n-way model matching? The answer is simple. Models can be large. And usually existing approaches do not scale well. As a solution, we present Raccoon, a scalable n-way model matching algorithm. And the basic idea of Raccoon is that fewer element comparisons lead to a faster matching runtime. To do so, Raccoon has three phases, while the first two phases focus on reducing the number of comparisons that are required in the third phase, which conducts the actual matching. Let's have a closer look at these phases. So first, Raccoon maps elements to points in an n-dimensional vector space. For each element in the models, we apply a vectorization function that yields a numerical vector representation of this element, and the elements can therefore be mapped to any point in this vector space. And the hope here is that similar model elements are mapped to points that lie close to each other in this vector space, while elements that are unsimilar to each other are mapped to points that are more distant in this vector space. We can then make use of this mapping in this vector space in the second phase by applying a nearest neighbor search in the n-dimensional vector space in order to find the nearest neighbors of each element. And each nearest neighbor represents a possible match candidate. So at this point, we do not make the actual match decision yet. It's just that we collect suitable candidates for matching later on. This is the input for the third and last phase, where we compare and match neighboring elements based on their distance in the tree, in the vector space. Now the question remains, how well does Raccoon scale actually in practice? And to answer this question, we conducted an empirical evaluation for which we required two things. First, a prototypical implementation of Raccoon, Here we, for now, just implemented a rather generic approach, which does not really consider specialized model types or special properties of models. It is only concerned with simple element properties and models. And second, we need a suitable data set, which comprises model sets of varying size in order to see how the scaling goes with growing model size. As for the data set, we consider ArgoUML as a basis. ArgoUML is a data set comprising model variants that stem from our product line. And variants here are rather similar to each other. And we also have unique identifiers available among these models, which can be used to evaluate the matching result. In order to get additional model sets with fewer elements of varying sizes, we randomly remove elements from ArgoUML, and thereby, in the end, we receive ArgoUML subsets, which size range from 1 to 95% of the original dataset. And of course, we have 100% in form of the original variants. So let us have a look at the results. How well does Raccoon scale? Here we compare Raccoon with two other algorithms. First, the n-way matcher NWM by Julia Rubin and Masha Cicic, and two pairwise matching approaches that differ in the ordering of the models. So the first pairwise approach simply orders the models from smallest to largest, and the other one from largest to smallest. And internally, these pairwise matchers use weighted set packing in order to maximize the match quality between two models at a time, yielding a local optimum. And when we look at the results, first we can see that the runtime of NWM is cut off for models subset sizes of more than 40%. This is because we implemented a 12-hour timeout for each experiment. We ran a lot of experiments, so we had to have some kind of timeout. Otherwise, it would take forever. It would take months to be calculated. And NWM wasn't able to present us a result after for models of larger sizes. Raccoon, on the other hand, was able to scale for all subsets, but it is still slower than the pairwise approaches here. So let's have a look at the precision and the recall of these matchers, because if pairwise and the n-way matchers are well, the same by matching quality, then we do not really need an n-way matcher. So are the formed matches correct? And here we see a decisive difference between the n-way matchers and the pairwise approaches. This is a problem of pairwise only considering two models at a time. So worse models are formed, which makes it difficult to find better models matches later on. And Raccoon and NWM, they show quite similar results in terms of precision. And when considering whether all relevant matches have been found, we can see that Raccoon achieves a recall of almost 1 across all subsets, meaning that it's able to find all necessary matches for an element, while the other approaches drop quite a bit. Especially NWM here, this was to our surprise actually, and we believe it is due to an internal heuristic which is used that splits up already formed matches with the goal of actually having higher match quality, but we believe that it does not work here in this case. So in summary, Raccoon scales while still being slower than pairwise. However, the precision and the recall are much better across all subsets than what we saw with pairwise approaches. And why is Raccoon so fast in the end? And how many comparisons are actually saved? We checked this on ArgoUML and all other data sets which we considered in our paper. And here for ArgoUML, we can see that Raccoon was able to reduce the number of required comparisons by 99.3%, always in relation to a full n-way matching. So a fully connected graph, so to say. For future work, we plan on specializing Raccoon on different domains. So as I mentioned earlier, at the moment it's quite a generic implementation, and we do not account for specific model type properties which can be useful in order to match models and elements more precisely. We want to extend the Raccoon to end-to-end element matching. At the moment, we limited ourselves to one-to-one matching because the other matchers also just stick to one-to-one matching, and we wanted to stay comparable. And lastly, we want to explore scenarios with interactive matching, meaning that instead of yielding a definite result of matches, Raccoon just yields a set of match proposals, which can then be accepted or rejected by a developer or by another program which calls Raccoon. And based on acceptance or rejection, new model matches are proposed, and new element matches are proposed. So in summary, we consider domains in which model-driven development is applied and multiple variants of a model exist. We propose a scalable n-way model matcher Raccoon as a solution to model matching in these domains. Raccoon is scalable because it applies a nearest neighbor search in an n-dimensional space to reduce the number of required comparisons during the matching phase. And our empirical evaluations show that Raccoon does scale for large model sizes and achieves higher precision recall than the other matches. Thank you for your attention, and I'm done and ready for questions.